3I Atlas didn't just pass through our solar system. It changed inside it. The latest images, quietly released through a delayed ESA data drop, show something no one expected. A geometry that isn't random, thermal signals that pulse in intervals, a pattern buried inside the green coma, a structure, not chaos. Before we dive in, subscribe if you're new here. Let me know in the comments where you're watching from, and the exact time right now. I'm tracking the global map of when this story reached each of you. Here's what we found when the veil was lifted frame by frame on a comet that shouldn't be shining, shouldn't be pulsing, and definitely shouldn't be slowing down. In the realm of deep space observation, not every breakthrough comes from a primary instrument. Sometimes it's a calibration frame, a background scan meant to fine-tune optics that reveals the most unsettling truth. That's how this began. On October 3rd, at precisely 4:26 UTC, a low-priority exposure from the Trace Gas Orbiter's side-mounted infrared imager was uploaded to the ESA's internal archive. It was part of a standard instrument calibration sequence, one of hundreds processed that week. The frame should have been routine: a faint star field, low solar interference, background noise correction. But buried inside the coma of 3I Atlas was something that shouldn't be there, something with edges. Zoomed and enhanced by the post-processing team in Darmstadt, the data revealed a faint internal geometry. Not gas, not dust. A soft arc of reflected light, nested too neatly to be coincidence. Analysts ran the standard false color spectrum overlay and applied digital filters to remove glare from solar backscatter. What remained was chilling. A narrow, symmetrical ridge running along the inner coma's central axis. Its brightness curve matched nothing previously observed in interstellar objects. At first, the assumption was artifact, an imaging glitch or diffraction spike, but that theory fell apart quickly. Multiple exposures from adjacent instruments, including a secondary scan from Mars Express, independently confirmed the structure. The anomaly was real, but the structure wasn't the only thing out of place. Alongside the ridge, a series of notches appeared in the coma's luminosity profile. Regular dips in brightness at fixed radial intervals. When modelled three-dimensionally, these dips aligned along a spiral trajectory, as if material was being ejected in timed intervals, not continuously. That's not how comets behave. Sublimation from solar heating is messy, turbulent, and full of stochastic noise. This wasn't noise, it was rhythm. Within hours, ESA's spectrometry team reran the data, using higher resolution algorithms normally reserved for planetary atmosphere scans. The spectral return shocked even the most conservative scientists on the team. Not only did the structure reflect light in narrow bands, it did so at intervals that matched coherent scattering, something more akin to engineered materials than amorphous dust or ice. Meanwhile, a separate team compared these findings to archival data from Oumuamua and Borisov, the only two other confirmed interstellar objects. Neither showed anything close to this level of internal consistency or structural coherence. Borisov was chaotic, fragmenting as it neared the Sunday. Oumuamua tumbled unpredictably and showed no visible coma at all. 3I Atlas, however, appeared organized, stable, evolving from the inside out. There was one more detail that pushed the team into full alert mode. The internal arc, only visible in a narrow ultraviolet band, appeared to pulse. Not flicker, not flash, pulse. The brightness rose and fell every 11.2 hours with an amplitude change of nearly 2.4%. At first, it seemed like a rotation artifact, perhaps a reflective region catching sunlight at different angles. But then, when that same pulse showed up in thermal readings taken by the James Webb Space Telescope days later, it became clear this was not a surface effect. The pulse was volumetric, coming from within the coma, and perhaps from within the nucleus itself. This forced a deeper question. Is 3I Atlas simply reacting to its environment, or is it reacting on schedule? To the public, the new photo set looked like nothing more than another fuzzy green blur with a halo. But within the data community, word was already spreading. The phrase, structured anomaly, had quietly entered circulation. Whatever this is, it's not just ice and dust anymore. And this frame, the one that was never supposed to reveal anything, may have been the first accidental look inside something far older and stranger than we expected. It began as a subtle flicker so faint that early algorithms discarded it as photometric noise. But over time, the pattern refused to disappear. In exposure after exposure, telescope after telescope, a rhythmic change in brightness pulsed through the coma of 3I Atlas. At first, no one paid it much attention. Variable brightness isn't uncommon in comets. As they rotate, certain regions reflect more sunlight than others, but this was different. The pulse wasn't chaotic, and it didn't match any known spin rate. It was symmetrical, regular, almost metronomic. The first confirmation came from a team at the Las Campanas Observatory in Chile, using high-sensitivity CCDs to observe the green glow of the coma. Over a 72-hour period, they detected a repeating cycle of brightening and dimming each wave lasting precisely 11.2 hours. Curious, they passed their data to ESA, whose instruments had been observing 3I Atlas in near-infrared and thermal bands. The same pattern appeared there too. Different wavelengths, same pulse. That's when scientists realized they weren't looking at a surface effect. This wasn't caused by rotation or a reflective patch turning toward the sunday. The signal was deeper embedded in the coma, radiating outward from within the nucleus like a wave passing through mist. This led to the first theoretical model, internal resonance. In some asteroids and icy bodies, thermal gradients can cause cyclic pressure changes beneath the crust. These create expansion and contraction phases, which sometimes modulate gas release. But even that idea fell short. The temperature of 3I Atlas's core wasn't changing fast enough to account for such a perfect rhythm. Moreover, no visible outgassing accompanied the pulses. There were no jets, no plumes, no rotational wobble, just light changing in perfect intervals. The James Webb Space Telescope, already tasked with observing the comet's spectrum, offered a breakthrough. On September 28th, its NIRCam captured time-lapse data of the pulse across the 3.5 micron range. And within those pulses, scientists discovered something stranger still: frequency doubling. Every fifth cycle contained a harmonic ripple, a brief secondary flare exactly halfway between the usual peaks. Nature can create rhythm, but nature rarely creates harmony. Astronomers scrambled to find analogues. They combed through decades of comet observations. They analysed Oumuamua, Borisov, Halley. Nothing came close. Even artificial satellites designed to pulse at regular intervals don't maintain this level of phase-lock stability without guidance systems. This raised an unsettling possibility. Either 3I Atlas was behaving in a way never before seen in natural bodies, or it wasn't acting entirely alone. That word acting began creeping into briefings and internal memos. Nobody was ready to say it outright, but behind closed doors, some researchers wondered, could this be a signal? Most dismissed the idea. The pulse wasn't encoded in binary. It didn't carry frequency modulations typical of communication attempts, but it did suggest control, or at the very least, memory. Something about this object was timing its energy release with astonishing precision. One final observation sealed the mystery. Amateur astronomers in Australia and New Zealand, using stacked long-exposure images, noticed that the pulses weren't just visual, they affected the shape of the coma. The green cloud surrounding 3I Atlas seemed to expand slightly with each brightness wave, then contract, like breath. It was almost biological. The scientific community is still divided. Some argue it's a deep thermal resonance, a natural yet unobserved phenomenon. Others think it's related to internal gas pockets interacting with structural features beneath the surface, and a few are no longer willing to call it coincidence. For now, we call it what the data shows: a pulse. 11.2 hours, unbroken, unexplained, and still beating. It was a single spectral signature that changed the tone of the investigation, one that didn't make sense on first reading. When researchers at the European Southern Observatory ran a high-resolution spectrographic pass on 3I Atlas, they found a surprising chemical fingerprint: vaporized nickel. At first, this wasn't shocking. Nickel is often embedded within the metallic cores of asteroids and comets. It's heavy, durable, and forms naturally alongside iron in the early stages of planetary formation. In fact, whenever we detect nickel in space, we expect to find iron right beside it. But not this time. The spectral lines showed a clear and elevated presence of neutral and singly ionized nickel atoms, bright, distinct, and sharp. but the corresponding lines for iron, both Fe1 and Fe2, were completely absent. Not faint, not obscured, absent. This set off alarms across multiple observatories. One lab in Japan initially flagged their own reading as faulty and recalibrated the instrument, but the anomaly repeated. Then, the team at Gemini South in Chile confirmed the result independently. The nickel was real, and the iron wasn't just missing, it had never been there. That's when the comparisons began. In our solar system, nickel and iron are cosmological twins. They're forged in the hearts of dying stars, thrown out into space together during supernova explosions. Over billions of years, those elements clump, differentiate, and form the cores of rocky planets, moons, and some large asteroids. The presence of one without the other, especially in large quantities, is virtually unheard of. Even more intriguing was the state of the nickel. Spectroscopy showed it wasn't bound inside minerals or dust grains. It was in the gas phase, ionized and drifting free, like vapor in a backlit mist. That would require extreme heat or some exotic sublimation process, especially at the distances where 3I Atlas was observed. But the infrared readings didn't show any corresponding temperature spikes. There was no thermal justification for metal to be vaporizing in space. So how was this nickel getting out? And why was it so cleanly separated from iron? The leading theory at first was mineral sorting, that the comet originated in an ancient system where some selective geological process filtered the materials in layers. But even in the most chemically diverse systems we know, complete decoupling of nickel and iron just doesn't occur. Then came the suggestion that stopped the conversation cold. This wasn't natural sorting at all. It was selection. Some researchers, cautiously and only in private, began to hypothesize that 3I Atlas may not just be holding nickel. It may have been using it. Nickel, especially in its pure metallic state, is known to have valuable electromagnetic properties stable under heat, corrosion-resistant, and capable of conducting in extreme conditions. Was this object carrying a load of refined material? Or worse, was the nickel part of an engineered structure now degrading into space? If that sounds extreme, consider this. The vaporization wasn't random. The emission remained steady across observations, suggesting a uniform layer of nickel releasing at a controlled rate. The material wasn't bubbling out, it was fading, as though it had been exposed intentionally or activated under certain light conditions. One researcher described it as like watching insulation burn off. The idea of engineered metals is not a conclusion, but it's now an open question. ESA has quietly added new filters to its next round of observations, focusing specifically on elemental separation and isotope ratios. Because if the nickel is pure, and if the missing iron is truly missing, not just hidden, it would mean that 3I Atlas doesn't just come from a different place in the galaxy. It comes from a different kind of place, one where matter itself is processed differently. Whatever the source, this comet just gave us a metal signature we've never seen in nature, and the implications may be heavier than the element itself. In orbital mechanics, precision is everything. The slightest deviation, just a fraction of a degree, can rewrite an object's future. Most comets drift along predictable curves, nudged gently by solar gravity, shaped by their momentum and mass. But 3I Atlas has never followed the expected script. The tilt was first noticed by an intern at the European Space Operations Center in Darmstadt, Germany. A graduate analyst named Felix Morvan was reviewing astrometric data from ExoMars and comparing it to predicted paths provided by the JPL Horizon system. At first, the discrepancy was so small it looked like rounding error less than 0.01 degrees off the projected arc. But over the next 3 data entries, the error persisted. Then, it grew. By the end of the 72-hour cycle, the tilt in the trajectory was measurable. A consistent, slow curvature, downward, inward, toward the plane of the inner solar system. This wasn't a chaotic deflection like we sometimes see with small debris impacts or gravitational encounters. This was something more deliberate. Most hyperbolic objects pass through our system on a one-way trip, barely bending their path as they slingshot around the Sunday. But 3I Atlas wasn't just slowing down, it was changing direction. At first, scientists proposed solar radiation pressure as the culprit. Photons can push on particles, ever so slightly adjusting a comet's path. But the observed tilt didn't align with solar radiation vectors, nor did it match up with the weak gravity of nearby Mars, which it had recently passed. The object should have curved outward, Instead, it curved in. That alone might not have raised concern, but the direction of the tilt held something more curious. It aligned precisely with a vector running between the Sun and Earth's orbital path. This didn't prove intention, yet the angle was unsettling. ESA's internal simulations, run across 500 variations of comet mass and coma density, failed to reproduce the observed tilt under any known natural conditions. No solar wind interaction, no thermal venting pattern, no known mass distribution could account for the steady deviation. And perhaps more importantly, no change in the coma's visible structure accompanied the tilt. There were no violent jets, no sudden flares. The arc of motion changed, but the body appeared calm. This opened the door to a controversial possibility: micro-vector adjustment. In spacecraft navigation, small burns can create subtle course corrections, precise, efficient, and nearly invisible to the naked eye. Some began to suspect 3I Atlas might be exhibiting something similar: small-scale directional shifts, without corresponding visual signatures. No gas jets, no thermal plume, just motion. Controlled, measured. Was this just a natural mass undergoing a perfect alignment of random forces? Or was the object responding to gravity, to radiation, to something we haven't yet identified? A few theorists floated a wilder possibility: that 3I Atlas was not merely drifting toward the Sun, but entering a targeted descent arc, a maneuver used in orbital insertion. The kind of trajectory an interplanetary probe would follow to enter a stable solar-bound orbit rather than escape. If true, this would mark the first time any interstellar object has transitioned from a hyperbolic flyby into a bound elliptical path without external intervention. That kind of orbital shift requires energy, a loss of kinetic velocity, a push against momentum. Something had to be at work. But what? The object shows no propulsion. It has no visible sail. And yet, here it was altering course ever so slightly, but precisely enough to draw a new conclusion. 3I Atlas wasn't just visiting. It might be staying. That realization sent a quiet ripple through international observation teams. Trajectory files were renamed from Object Exit Phase to Capture Possibility Model. For the first time, 3I Atlas appeared in datasets flagged for persistent orbital recheck. In the language of spaceflight, that's the moment something stops being a curiosity and starts being a candidate. It happened quietly. No press release, no conference, just a quiet update in a back-end metadata field inside the European Space Agency's object tracking catalogue. 3. I-Atlas was no longer labelled Interstellar Transient. Instead, its classification tag had changed to Capture Candidate, pending orbital confirmation. In the public-facing portal, this shift went unnoticed. The object's coordinates and flyby estimates were still visible, but within ESA's internal tracking system used by flight engineers, mission planners, and cross-agency analysts, the change was significant. And it wasn't the only one. Data permissions had shifted. Within hours of the reclassification, access to real-time telemetry from the ExoMars Trace Gas Orbiter was restricted to a handful of encrypted user tiers. Amateur astronomers who had previously downloaded near-live ephemerides from the planetary data system reported 404 errors. Even within ESA, researchers outside specific mission teams found their credentials revoked from certain folders, and nobody would say why. Historically, ESA and its NASA counterparts have embraced radical transparency with space data. From Mars Express to the Rosetta mission, early images and raw measurements are typically released within days. But after 3I Atlas passed Mars, everything slowed down. No new images, no updated spectral scans, no orbital deltas, and then the reclassification. So why would an object, first considered an outbound traveller, suddenly be tagged as a capture candidate? The answer, as always, lies in the math. When the post-Mars telemetry was run through updated orbital solvers, the outputs were unexpected. The hyperbolic excess velocity of 3I Atlas, its speed relative to the Sun, was dropping, ever so slightly but consistently. It was no longer on a clean outbound arc. Instead, it was curving, flattening into a path that suggested long-term residency within the solar system. This isn't supposed to happen. Interstellar objects don't slow down. If anything, they speed up as they fall toward the Sun. then whip around in a gravitational sling and exit forever. Only a powerful counterforce, something subtracting from their energy budget, could result in the kind of slow deceleration that analysts were now seeing. At first, the official explanation was outgassing that jets of vapor from the comet's sunlit side were nudging it inward. But no such jets had been observed. The coma showed no sign of asymmetry, and as discussed in previous chapters, the surface remained cold and inert in thermal scans. With no confirmed cause for the trajectory change, the orbital status was quietly updated. But the word capture carries weight in astronomy. It implies not just a change in motion, but a change in intent. That's why the reclassification sent subtle shockwaves through partner agencies. Within days, NASA's Goldstone radar shifted resources, assigning extra tracking windows to 3 IATLAS. The UAE's Hope orbiter, which had not previously focused on the object, began silent calibration scans in the region, and China's Tianwen-1 stopped transmitting deep space telemetry altogether, citing data prioritization restructuring. One researcher at ESA, speaking anonymously, put it this way: "We've moved from watching it go to watching it stay." This shift, this reclassification, is more than a bureaucratic adjustment. It marks a psychological turn. As long as 3 IATLAS was outbound, it was someone else's problem. Something ancient, passing briefly through our sun's light before vanishing back into the dark. But now, it's entering the neighborhood, and for astronomers, that raises fundamental questions. If it was meant to pass through, why is it decelerating? If it was never meant to leave, what is it doing here? ESA hasn't made an official comment since the update, but in the metadata, the new status remains. Not a transient, not a flyby, just a single line: capture candidate, inbound trajectory under review. Sometimes, it's the small lines of text, the ones buried deep in a table, that whisper the loudest. For most comets, a spectrogram is a chaotic rainbow. Peaks and valleys of molecular emissions, tangled lines from ionized gases, and irregular patches from dust scattering. Every band tells a story of water, carbon, dust, and heat. But when 3 IATLAS was scanned across the visible and near-infrared spectrum, it told a story no one had seen before, because in between the expected emission lines, there was nothing. Not silence. Absence. ESA's early imaging scans from the Trace Gas Orbiter detected the standard signatures of a comet: diatomic carbon, cyanogen, and faint hydrogen. But when analysts pushed the data deeper, extending into mid-infrared bands and ultraviolet, they hit gaps. Entire swaths of spectrum that should have shown noise, background scatter, or weak emissions were instead flatlined. These weren't underpowered signals. They were spectral holes, regions where no photons were being detected at all. To understand how strange that is, it helps to know what should be there. Every known gas, mineral, or dust in a cometary coma reflects or emits across multiple bands, even if faintly. Thermal jitter, solar reflection, and molecular excitation normally guarantee at least background noise across most of the electromagnetic spectrum. But 3 IATLAS showed clean voids, perfectly cut sections of silence across wavelengths where gas should glow. The first thought was instrumentation failure. The ExoMars Omega spectrometer was recalibrated. Its detectors were rechecked. Then, the readings were cross-validated using independent data from NASA's James Webb Space Telescope and the Subaru telescope in Hawaii. All 3 instruments confirmed the same pattern: missing bands in the 3.2 to 3.5 micron range, again near 7 microns, and most unnerving between 900 and 950 nanometers. That last one was particularly troubling. Near-infrared reflectivity in that range is a hallmark of carbon-rich dust, one of the most common materials in comet tails. To have it completely missing means either the carbon is absent, or something is masking its signal. Some scientists proposed thermal absorption layers dense inner pockets of material that swallow heat. Others suggested exotic dust grains coated in volatile materials that deflect certain wavelengths. But those models required temperatures and chemical environments that didn't match the coma's observed behavior. Then a bold idea emerged: spectral cancellation. In engineered materials, especially those developed for stealth applications on Earth, it's possible to layer surfaces in such a way that incoming wavelengths are absorbed and phase cancelled, essentially deleting their reflection. It's used in radar cloaking and high-end optics, but in nature, it's vanishingly rare. Could 3I Atlas possess a surface or inner shell structured to suppress select wavelengths? If so, the next question is why? Some argued that if the object were shedding mass from within a degassing nucleus or fractured core, it might expose layers that naturally filter light due to their density or crystal alignment. But again, the missing bands were too clean, too evenly spaced. The gaps followed a pattern, not a messy geological fracture, but something eerily regular. It was at this point that a few data scientists began overlaying the missing spectral bands, not on a time axis, but spatially. They charted where, in the coma, each spectral hole appeared most strongly. The result? A radial geometry, each silent band aligned along a spoke-like pattern, radiating outward from the center in symmetrical arcs like slices of a wheel. It wasn't just which wavelengths were missing, it was where they were missing from. No natural gas cloud should have symmetry like this. Not at this scale, not with this precision. Of course, the idea of structure remains speculative. Nothing in the images shows a solid body. There are no visible struts, no skeletons. But the spectral geometry suggests something real. Something internal is shaping the light, not just reflecting it. In astronomy, you rarely discover something by what's not there. But with 3I Atlas, that's exactly what's happened. Where there should be brightness, there's darkness. Where there should be noise, there's silence. And in that silence, we may be seeing the outline of something no one expected to find inside a comet. It showed up on just one image. Not a flare, not a streak, just a faint, impossibly smooth curve buried within the coma of 3I Atlas, like the shadow of a spine behind a veil. The frame came from the Goldstone Solar System radar during a passive reflectivity scan on October 6th. Unlike traditional optical telescopes, Goldstone listens, mapping, returning radio waves bounced off distant objects to reveal their density, shape, and sometimes motion. When technicians rendered the backscatter map from 3I Atlas, they noticed something that didn't belong. A single internal arc, symmetrical and continuous, nested entirely within the green cloud of the coma. At first it was dismissed as noise. Cometary comas are full of turbulence, swirls of gas, pockets of density, transient folds of dust. Artifacts are common, but this curve was too perfect, too smooth. It maintained an even radius over a 400-kilometer stretch, with a reflectivity gradient that didn't taper like gas. It held steady, like a skin, and it didn't move. Across 3 scans spaced 6 hours apart, the arc remained fixed relative to the core. While the surrounding gas shifted and blurred as expected, the arc stayed centered, unchanged. This was not turbulence. It was structure. To be clear, this wasn't a solid object. Nothing opaque. The arc wasn't casting a shadow or blocking the coma, but it was redirecting signals. Subtle interference patterns in the returning radar suggested a boundary of different dielectric properties, meaning electromagnetic waves were interacting with something denser than vapor, but not metallic, something semi-permeable. Goldstone analysts ran layered reconstructions and applied radar tomography, similar to methods used on asteroid Bennu and comet 67P. The internal arc didn't follow the chaotic, jagged patterns those objects exhibited. Instead, it resembled a torus, a donut-shaped ring, thin and embedded, surrounding the central body of 3I Atlas like a collar. The proportions were oddly balanced, 31 kilometers wide, 4 kilometers thick, equidistant from the core center across all data points. No known natural coma has this kind of embedded, symmetric density ring. Not even in high-activity comets like Hale-Bopp or Hyakutake. So what could it be? Some proposed a relic, an old shell of denser material trapped in the object's gravitational well, similar to a dust ring, but the curvature was too tight, and there was no indication of separation from the core. Others speculated that it was a rotating outflow boundary, a toroidal shockwave from symmetrical venting. But once again, the coma showed no jets, no spin turbulence, no motion. Then came the most controversial theory, that the arc was not a result of 3I Atlas's behavior, but part of its design. If the object were more than a random mass, if it had internal architecture, then a toroidal structure could serve multiple roles, regulating material outflow, controlling spin, or even acting as a resonance chamber to maintain internal pressure. A few researchers pointed to the regular pulse discussed in Chapter 2, the 11.2-hour rhythmic brightening. The arc, they proposed, could be the origin of that pulse. A pressure ring flexing in and out with each internal cycle, like the diaphragm of a speaker. Or perhaps a stabilizing ring, keeping internal mass aligned during micro-adjustments in trajectory. Still, these remain theories. There is no conclusive image, no direct proof. Just the echo of structure radar shadows, wave interference, and an arc that doesn't move. What makes it so compelling is how isolated the arc is. There's no web of fractures, no irregularities, no hints of collapse. Just a single, mathematically precise band, existing where no natural ring should. And in a cosmos filled with chaos, precision is often the loudest anomaly. Whatever it is, the internal arc has changed how scientists model 3I Atlas. It's no longer treated as a drifting body of gas and dust. It's now charted as a multi-density object, one with core zones, phase boundaries, and possibly internal engineering. Because when structure appears inside silence, we have to ask, was it formed? Or was it built? It wasn't the brightest part of the photo that drew attention, it was the absence of light. In mid-October, a sequence of long-exposure images was captured by a privately operated telescope array in the Atacama Desert. The array, originally designed for exoplanet transit studies, had recently been reconfigured to track the slow inward drift of 3I Atlas. With its extreme dry air and high altitude, Atacama provides some of the clearest night skies on Earth. And in one frame, under low light and deep infrared processing, something startling appeared. A shadow, cast from inside the coma, trailing into the outer gas cloud like the wake of an invisible object. Shadows aren't unusual in astrophotography. Bright stars cause diffraction spikes. Dust grains block light. But this was different. This shadow wasn't cast from an external source, it was internal, projected from a denser region within 3I Atlas's coma onto the surrounding vapor. That's not supposed to happen. Comets are chaotic clouds. Their interiors are turbulent and full of random flows. Any shadows they cast tend to be faint, irregular, and momentary, caused by passing debris or dense jets of escaping gas. But this shadow was symmetrical, stable. It held its shape over several frames, maintaining a sharp edge across thousands of kilometers of dispersed dust. To confirm the observation, independent data was pulled from the Gemini South telescope, which had observed 3I Atlas at roughly the same time from a different continent. After recalibrating the light curves and cross-referencing the angle of solar incidence, the same structure emerged, a faint, wedge-shaped void in the gas cloud, precisely opposite the Sunday. It was a cast shadow, and it meant one thing: something inside the coma was blocking light, but nothing solid had ever been detected inside 3I Atlas. That's when scientists returned to the Goldstone radar data from the previous week, the same data set that revealed the internal arc. When reprocessed through high-contrast interference mapping, a new feature appeared, a localized area of elevated reflectivity in the same direction as the optical shadow. It wasn't large, maybe a few kilometers across, but its signal matched something dense, something with shape, and more importantly, something that wasn't transparent. One possibility raised was a collapsed core fragment, an unusually dense region of the nucleus that had broken off, but remained trapped within the coma, held in place by gravity or cohesive forces. But there was no turbulence around it, no disruption, no outgassing. Others proposed a more exotic idea, a subsurface mass, a kind of internal scaffold, like a ring or disk, buried beneath the flowing gas, but structured enough to interrupt light paths. A partial shell, or even a frame, but it was a third idea that shook the internal discussions at ESA and NASA. What if the shadow wasn't being cast from matter, but from geometry? In certain models of light propagation, electromagnetic waves can be scattered not just by physical objects, but by phase-shifted fields. This happens around highly structured materials, including metamaterials and coherent plasma shells. It's been observed in advanced optics labs on Earth. Could 3I Atlas contain an invisible interface, a non-solid boundary that refracts or bends light sharply enough to cast shadows onto its own outer layers? It's speculative, but the precision of the shadow, the way it held still while the rest of the coma shifted, suggests stability, deliberate form, and perhaps even orientation, because the shadow always pointed away from the Sunday aligned. Steady. For those watching closely, this was no longer the behavior of a passive object. This was an object with edges, with intentional occlusion, and possibly with a surface buried deep beneath the visible layers, but just reflective enough to momentarily betray its presence. In astronomy, a shadow can be more revealing than light, because only structure creates shape, and for 3i Atlas, this may be the first true glimpse of something inside not imagined, not inferred, but visibly there. Most cometary bodies rotate in hours. Some tumble chaotically, spinning like fragments of ice caught in turbulence. Others roll with regularity, revealing patterns in their brightness curve that help astronomers deduce their spin rate, axis tilt, and internal cohesion. But 3i Atlas doesn't spin the way it should. In fact, it barely spins at all. The rotation was first suspected to be slow when early photometric data showed a delay in brightness variation. As the object approached Mars, observatories across the globe measured tiny fluctuations in the comet's overall luminosity. Normally, such fluctuations are tied to surface reflectivity, ice patches, gas vents, shadowed terrain. As a comet rotates, these features face the sun at different angles, causing a rhythm in how bright or dim the object appears. For 3i Atlas, the rhythm was unusually long. Over the course of several nights, data from telescopes in Spain, Chile, and Japan began to converge on a surprising figure, a rotation period of approximately 40 hours. That's nearly 2 Earth days for a full spin. On its own, slow rotation isn't impossible, but it's rare, especially for an object ejecting significant mass. Most active comets spin faster because of momentum from outgassing. As material jets off from one side of the nucleus, it imparts torque, gradually spinning the body faster. It's like a sprinkler effect, and it's seen in comets large and small. But 3i Atlas was active and yet barely turning. Its coma was expanding. Gases were venting in symmetrical patterns. The object's green glow intensified by the day, but the body itself remained almost motionless in terms of rotation. That disconnect between activity and spin sent researchers scrambling for answers. One early explanation was mass. If the nucleus were exceptionally dense, it could resist the spin-up normally caused by gas ejection. But this idea collapsed when mass estimates came in. Based on coma density and gas dispersion rates, the object couldn't be more than a few kilometers wide, too small to have that much inertia. Another theory was that the rotation axis might be pointed almost directly at Earth, giving the illusion of minimal rotation. But Doppler spectroscopy ruled this out. The spectral lines of escaping gas were symmetrical in all directions. The body wasn't spinning edge-on, it was barely spinning at all. Then came a stranger idea. Something is keeping it stable. Some objects in the universe have spin-dampening mechanisms. Artificial satellites, for example, use gyroscopes or momentum wheels to control orientation. In nature, tidal forces can slow a moon's rotation if it orbits close to a planet for long enough. But 3i Atlas isn't near anything massive. It's not being pulled or torqued by any known body. So, why is it so calm? The pattern deepened when long-exposure imaging from the Hubble Space Telescope revealed a curious flow. The coma expanded uniformly, with no signs of spiral jetting or asymmetrical release. Even gas escaping from beneath the surface showed a baffling symmetry, like breath exhaled evenly from all directions. No twisting, no torque, no wobble. This leads to one of two conclusions. Either the object's outgassing is occurring perfectly evenly across its surface, a balance so delicate it's never been observed before, or 3i Atlas is regulating itself. It's an uncomfortable thought. Regulation implies control. Control implies coordination. And coordination, at this scale, suggests a structure capable of sensing, responding, and adjusting to maintain equilibrium. For scientists, it's still too early to make that claim. But among engineers and physicists used to spacecraft telemetry, the data feels familiar. When you see motionless symmetry in the midst of energy release, one instinct comes to mind: stabilization. Because nature rarely stabilizes perfectly, but machines often do. And in the case of 3I Atlas, the absence of spin might be the loudest motion of all. If there was a moment where everything changed, it happened near Mars. Before its close pass by the red planet, 3I Atlas had behaved exactly as expected. An interstellar object on a clean hyperbolic trajectory, approaching fast, glowing steadily, and set to slingshot past the sun before vanishing back into deep space. But after the Mars encounter, the story fractured. Telemetry gathered before September 28th showed a clear arc, an outbound curve with all the hallmarks of a gravitational assist. But just days later, updated tracking revealed a deviation. Subtle at first, then unmistakable. The object wasn't slingshotting. It was bending its path, flattening, slowing, curving inward. The first to notice was an astrodynamics group at the University of Padua, running routine simulations of interplanetary flybys. They flagged a mismatch between expected and observed ephemeris data. When ESA ran the same numbers using ExoMars and Mars Express, the anomaly was confirmed. Something happened near Mars, something that changed the future of 3I Atlas. The object's velocity had dropped by approximately 0.003 meters per second squared, a minuscule deceleration by human standards. But in space, such a change is monumental. Over millions of kilometers, it adds up. And more importantly, it's not a behavior that fits the profile of a cold, inert object coasting through a solar flyby. Deceleration implies force, and force requires a cause. Was it Mars? That was the first assumption. A gravity assist that didn't go according to plan. But when simulations were run backward, they showed that Mars's gravitational influence wasn't strong enough, and the object's trajectory hadn't come close enough to account for such a precise energy change. The numbers didn't align, so scientists looked elsewhere. Could it have been outgassing? A jet of vapor erupting from the sunward side of the object as it neared a new thermal threshold? Possibly, but the coma showed no such event. No plume, no asymmetric trail. The comet's expansion remained symmetrical calm, even. No observable momentum transfer. The absence of visual disruption ruled out fragmentation. What remained was deeply unsettling. A directional, low-intensity deceleration, without an observable cause, occurring precisely after the Mars flyby. Some began calling it the Mars signature, and then came the second anomaly. In an image captured by China's Tianwen-1 orbiter, an unusual reflection appeared just above the Martian limb, faint, brief, and inconsistent with sunlight. Analysts ran the frame through contrast enhancements and detected a backscatter event, possibly from radar or high-frequency emissions. The timestamp matched 3I Atlas's closest approach. At first it was dismissed as noise, but hours later, the Deep Space Network picked up an unexplained burst in the X-band, a short-lived pulse lasting less than 0.8 seconds, directly aligned with the object's path. Again, it could have been coincidence. Radio background noise is common, but in conjunction with a confirmed deceleration and a clean shadow image recorded 2 days later, the Mars flyby began to take on a different character, not just a moment of trajectory change, but a moment of interaction. Was the object responding to something? If 3I Atlas was inert, then the energy change must be explained externally. But no external event, no solar flare, CME, or local disturbance was recorded during that window. The Martian atmosphere was quiet. No known gravitational anomaly occurred, and yet, the object shifted course. More concerning was the precision. The trajectory after Mars aligned more closely with Earth's orbital plane, and though the object remained far from direct intercept, its decision to stay within the inner solar system, if one can use that word, occurred immediately after passing the red planet. That's why researchers now refer to this phase as the turning point. Not just a change in orbit, a change in behavior. Because before Mars, 3I Atlas followed the laws of physics. After Mars, it started bending them. In astronomy, light tells the truth. Every object in space reflects, refracts, absorbs, or emits light in ways that reveal its composition, movement, and shape. And one of the most well-understood behaviors is scattering the way light interacts with particles in a comet's coma. Small particles scatter light backward and sideways more than forward. It's basic physics. In a diffuse gas cloud like a comet's coma, sunlight enters, hits dust or ice, and bounces in multiple directions. The intensity depends on angle, wavelength, and the size of the particles. But with 3i Atlas, the brightest light wasn't coming from behind the object, it was coming from in front. This is the heart of the forward scattering paradox, a phenomenon that has confused observers since early October, when images from multiple observatories, including Subaru, Gemini South, and the JWST, began to show an unusual brightness pattern. Instead of lighting up from the trailing side, as comets typically do when sunlight reflects off their tails, 3i Atlas appeared most luminous on its sun-facing edge, an intensity that not only remained constant as it moved, but increased as it passed opposition. Initially, this was thought to be a fluke of timing, a temporary alignment. But as the days passed and the object continued its trajectory, the anomaly remained. The leading hemisphere of the coma, the front, remained saturated with high-energy light. The rest fell into dull gradients. That's not how dust scattering works. Comet tails are traditionally brightest after the sun hits them. Light bounces off particles and reflects toward Earth at a back angle. Forward scattering, while possible in rare cases, requires micron-scale particles suspended in a narrow angular band. It's an effect that shows up occasionally in exoplanet transit studies, not cometary objects. Yet with 3i Atlas, forward brightness wasn't occasional, it was persistent. So what was causing it? One idea suggested a high concentration of ultrafine dust at the front of the coma, tiny reflective particles densely packed in a symmetrical arc. But this explanation didn't match the object's mass loss rate. There wasn't enough material escaping to form a persistent forward shell. Another theory pointed toward plasma lensing, that ionized particles in the coma were forming a dynamic electromagnetic field capable of redirecting light toward observers, like a refractive envelope. But if that were true, we'd expect to see rapid flickering and dispersal. Instead, the forward brightness remained stable and centered. The final theory was more controversial. What if the light wasn't being scattered at all? What if it was being generated? Light emission rather than reflection would explain the intensity, angle, and persistence. Some kind of luminescence occurring at the leading edge of the object. Chemiluminescence, perhaps, or a high-frequency interaction between solar wind particles and an internal structure. But this raised a deeper problem. Luminescence requires energy input, and while sunlight provides plenty of that, 3i Atlas doesn't behave like a solar reactor. Its coma is cold. Spectral scans show no ion jets, no localized hotspots. And still, the light continues. In high-resolution frames taken from JWST, the glow isn't diffuse, it's concentrated, focused along a narrow crescent that hugs the object's orbital vector, like a bow shock but glowing, not heating, emitting, not deflecting. This breaks our models. Forward scattering is supposed to be weak, rare, and temporary, but in 3i Atlas, it's the dominant optical feature. And as it moves deeper into the inner solar system, this crescent of light grows more defined, sharpening like a blade of brightness at the front of an invisible mass. Some now suspect the presence of an optical system, something that manipulates the light around the object. A lens? A membrane? A shell of coherent particles aligned in formation? We don't know, but one thing is clear. This glow is not random. It follows geometry, it obeys structure. And it may be the first visible sign that 3i Atlas isn't just reacting to the sun, it's using its light. Every comet leaves a trail. Dust grains, ejected by solar heating, drift behind the object as it moves, forming the characteristic tail that points away from the sunday. This tail is chaotic, uneven, and constantly changing. The grains themselves are light, pushed outward by solar radiation, and swept into spiraling arcs by solar wind. But the dust surrounding 3i Atlas refuses to behave this way. It doesn't drift. It doesn't spiral. It stays. The anomaly was first flagged by amateur astronomers tracking the object's tail structure in early October. Images taken over multiple nights showed something odd. The coma remained uniform. There was no discernible tail, no trailing edge, no fading streaks behind the object as it moved. At first, the explanation was angle. Perhaps Earth's line of sight made the tail appear foreshortened, hidden behind the main body. But when compared to other comets at similar inclinations and trajectories, the lack of visible dust motion was still unusual. Then came the time-lapse data. Using stacked frames from the Gemini South Telescope and the European Southern Observatory, Analysts compiled movement maps of the particles surrounding 3 Iatlas over a 12-hour period. What they found was unprecedented. The dust remained suspended, locked in a symmetrical shell, showing almost no radial motion, not just slow static. In physics, this shouldn't happen. Dust, once released from a nucleus, is at the mercy of inertia, gravity, and solar radiation pressure. It moves. Even in weak jets, particles drift outward. But the material around 3 Iatlas hovered in place, as if trapped in a field. And it wasn't just dust from one side. The entire coma, hundreds of kilometers wide, remained in a stable configuration, like a snow globe frozen mid-shake. To verify this, scientists turned to polarization data. Polarized light can help determine the size, shape, and motion of microscopic dust. Normally, cometary dust scatters polarized light in uneven patterns, depending on how particles are spinning or drifting. 3. Iatlas's dust returned a perfect radial polarization pattern, as if the particles were not rotating, not tumbling, but aligned, equally spaced, consistently oriented, unmoving. This raised 2 immediate questions. 1. How is the dust staying in place? 2. What's holding it there? One theory suggested magnetic confinement. If 3 Iatlas were generating a localized magnetic field, perhaps through an interaction with solar plasma, it might create a kind of dust trap, holding fine grains in suspension. But there was no corresponding radio emission, no interaction signatures, and magnetic field modeling showed that the strength required would be orders of magnitude beyond anything observed in natural objects of this size. Another idea pointed to electrostatic levitation, similar to what happens on the Moon, where dust rises from the surface due to charge imbalances. But lunar grains lift and fall. They don't hover in spherical symmetry across a 3D volume. Still, the most disturbing hypothesis came from a small group of physicists who proposed this. What if the dust isn't being held? What if it's being placed, positioned, arranged, controlled? If the particles around 3 Iatlas are not random debris, but components of a structured medium deliberately kept in position, it could explain both their motionlessness and polarization. Like pixels in a display, or antennae in a phased array, a reflective skin, a sensor lattice, a shell of passive geometry. It's an idea without precedent in natural science, but it would explain the coma's behavior, and it would also link to other anomalies: the internal arc, the forward scattering glow, the shadow edge, because all of them suggest the same thing: structure inside chaos, and dust mundane. Drifting dust might be the very thing revealing it. If what we're seeing isn't the result of ejection but construction, then 3 Iatlas is not just an object passing through the solar system. It's an object doing something inside it. If 3 Iatlas had a heartbeat, we'd have missed it in visible light. It took infrared observations, quiet wavelengths beyond what the eye can see, to reveal something unexpected. A slow, rhythmic pulsing. A pattern not of rotation, not of outgassing, but of expansion and contraction, like something was breathing. The discovery came from the James Webb Space Telescope. Equipped with one of the most sensitive infrared instruments ever built, JWST captured multiple thermal snapshots of 3 Iatlas as it approached perihelion. These images weren't just static, they were time-sequenced, recorded over a 36-hour window to study thermal variation. The team expected to see the usual signs: heating on the sunward side, cooling on the dark side, perhaps minor fluctuations from gas jets. What they saw instead was a global thermal pulse. At intervals of approximately 11.9 hours, the entire infrared signature of 3 Iatlas would rise slightly, then fall, then rise again. This wasn't a surface effect. The pattern was coherent across the full extent of the coma. From the inner core out to the dusty boundary, the entire object appeared to inhale heat and then release it, like a living system. Initially, analysts suspected a calibration error. Thermal fluctuations in space can mimic biological rhythms if the sensor isn't corrected for orbital movement or solar angle. But when they ran comparisons across JWST's other targets that night, asteroids, background galaxies, and a few known comets, none of them showed this fluctuation. Only 3 Iatlas did, and it repeated with clock-like precision. To rule out coincidence, a separate team at the submillimeter array in Hawaii tracked the object using radio and thermal imaging. They found a similar pattern, though less precise due to atmospheric interference. Still, it aligned. The object's heat signature rose and fell in intervals that couldn't be explained by spin, solar exposure, or material shedding. So what's causing the pulse? The first theory proposed thermal venting. If gas were escaping from interior cavities at regular intervals, it could produce a minor increase in infrared brightness, but there was no matching movement in the coma. No pressure spikes, no jet-like behavior. The dust stayed still. Another idea explored internal oscillation, a kind of structural resonance, where heat builds within an enclosed shell and then radiates outward when a pressure threshold is reached. That would imply internal compartments, or at the very least, thermal boundaries inside the object. But a third theory pushed the discussion into new territory: phase-shifted emission. Some materials, especially engineered metamaterials, can store energy from external sources and release it at timed intervals. They don't just absorb heat, they modulate it. They breathe not because they are alive, but because their structure allows it. If 3I Atlas contains a lattice, membrane, or shell of such material, whether crystalline, plasma-bound, or metallic, it could explain the observed heat pattern. It wouldn't need to spin. It wouldn't need jets. The structure itself would act like a thermal capacitor, absorbing solar radiation, holding it, and then discharging it evenly across its surface. That would match the data. No directional heating, no wild bursts, just a rhythmic glow. The idea of thermal modulation leads to a deeper question. Why? What is the purpose of this pulse? Biologically, breathing serves one function: regulation, intake, and release, cooling and balancing. In engineering, it can be used to stabilize pressure or synchronize with external forces. In space, synchronization matters. Some researchers speculate the pulse might be coordinating with the solar environment timing itself to solar wind cycles, radiation thresholds, or magnetic field drift. Others think it could be interacting with Mars's magnetotail, or preparing for something ahead, because one strange detail keeps coming back. This breathing began after Mars. Before that moment, 3I Atlas's thermal signature was flat, static. But after its close pass, something woke up. The object became dynamic not just in orbit, but in behavior. Breathing may not mean life, but it does mean rhythm, and rhythm, in space, is rarely accidental. In the vacuum of space, cold is expected. But not like this. When NASA's Infrared Telescope Facility and the James Webb Space Telescope independently analyzed the thermal profile of 3I Atlas's core, they found something that didn't add up. Despite being closer to the Sun than Mars and actively emitting gas, the object's central mass, the nucleus, wasn't warming. It was cooling. The core of 3I Atlas remained colder than it should be, consistently measuring at 243 degrees Celsius, nearly 30 degrees colder than the surrounding coma, and just a few degrees above the cosmic microwave background. In simpler terms, it's radiating almost no heat at all. That's not possible, not naturally. Comets warm as they approach the Sunday. Their volatile ices, water, carbon dioxide, methane, begin to sublimate, releasing gas and dust in visible outflows. This process creates a halo of brightness, known as the coma, and while the coma can appear brighter due to sunlight scattering, the nucleus itself always shows a steady increase in temperature. But for 3I Atlas, the trend is reversed. In multi-band infrared studies, the coma glows faintly warm, but the core reads as a thermal sink. Instead of giving off heat, it's absorbing it, or more precisely, hiding it. This created what scientists now call the cold core mystery. Several theories were proposed. The first was composition. Perhaps the core was made of exotic ices or hyperreflective materials that resist heating. But spectral analysis didn't support that. No signature of ammonia, methane, or CO2 ice was dominant. Instead, the core appeared coated in a smooth, featureless layer, neither ice nor dust, but something that didn't match known comet materials. The second theory was insulation. Maybe the object had developed a crust of frozen material so thick it prevented heat from reaching the interior. But that still didn't explain the readings. Even highly insulated objects retain some thermal signature, especially under constant solar exposure. This core appeared darker, colder, and more thermally inert than any comet ever recorded. Then came the third theory. What if the core wasn't absorbing sunlight at all? What if it was reflecting it perfectly, or redirecting it intelligently? Engineers working on stealth satellite technology noted something familiar. Some military satellites use thermal cloaking materials designed to absorb minimal heat, emit even less, and mimic the temperature of the surrounding vacuum. The goal is to remain undetectable in infrared. What if 3i Atlas is using something similar? Some suggested the surface of the nucleus might be a super black material, not in the optical sense, but in thermal behavior. These materials don't just absorb light, they control how and when they release energy. If layered across a shell, they could effectively mask a warm object, making it appear colder than its surroundings. This theory only deepened when the Green Bank telescope scanned for sub-millimeter radiation from the core and found nothing. A dead zone. As if the core wasn't just cold, it was empty. But that's impossible. The coma proves there's material inside. Something is driving the expansion, feeding the gas, creating the shape. There is mass. There is activity. But thermally, the center acts like a void. One speculative theory called it a thermal cavity, a hollow structure with an outer shell that regulates emission, while hiding its internal configuration. It would be like standing next to a factory that makes no sound, no smoke, no vibration, yet constantly releases product. Still, none of this answers the key question: why would anything need to be this cold? In astrophysics, coldness is not just an absence of heat. It's a strategy. Cryogenic systems are used in computing, quantum control, particle physics, and data preservation. To remain this cold intentionally suggests a purpose, and that purpose may not be geological. It may be functional, because nature makes many things cold, but only technology keeps things cold on purpose. All comets emit. They vent gas, shed dust, scatter light, and radiate in infrared. These emissions are chaotic, natural, and mostly random, driven by sunlight, rotation, and internal pressure. In science, we read those emissions like smoke from a fire, messy but predictable. But with 3i Atlas, something is different. It's not just emitting, it's behaving as if it's signaling. In early October, a graduate research team at Caltech was mapping the object's ultraviolet outgassing patterns using archival data from the Hubble Space Telescope and ESA's solar orbiter. They expected a spherical flow of gases like CO2, H2O, and dust all ejecting in random bursts depending on internal heat and surface fractures. Instead, they found a repeating spatial pattern, CO. Two emissions from 3i Atlas were emerging in discrete zones at fixed intervals along the object's orbital path. Not all at once, and not rotational, these bursts followed a geometric rhythm. Roughly every 0.8 AU, a jet of gas would escape in a near-identical location relative to the Sunday. The pattern didn't match spin rate, perihelion heating, or known structural cracking. It looked, on paper, like something had been programmed. That was the first red flag. Then came the second. The Goldstone Deep Space Network, which had been tracking 3i Atlas via radar and narrowband radio reflectometry, picked up several brief anomalies. These weren't emissions in the traditional sense, not continuous signals, not telemetry, but momentary frequency spikes. Sharp pulses in the X-band and Q-band spectrum, lasting under 1 second, always occurring at intervals that matched the CO2 jets. To engineers familiar with spacecraft communication, the signature looked uncannily familiar. Binary gating. In binary gating, systems use high divided by low pulses to encode instructions on divided by off, yes divided by no, fire divided by delay. The emissions from 3i Atlas weren't strong enough to carry information in the classical sense, but their timing and pairing with physical events made it appear as though the object wasn't just releasing material, it was executing a sequence. This led to a hypothesis few dared voice publicly. Are we looking at instructions, not emissions? If each gas release isn't random but part of a controlled sequence, if the pulses of material are timed to specific positions, responding to solar input or orbital mechanics, then what we're seeing might be less like a comet and more like a script, a program unfolding step by step. Of course, this is dangerous territory. The risk of projection is high. In chaos, Patterns always emerge, but the consistency across instruments, locations, and wavelengths made even the most skeptical scientists pause. It wasn't just the gas, it was how the gas moved, where it moved, when it moved, and that it seemed to be waiting between each event. One possible natural explanation is phase transition physics, that the interior of the object contains layers of frozen gases, releasing under strict pressure thresholds. But that theory collapses under one key observation. The emissions remain in perfect solar alignment even as 3I Atlas changes orientation. They don't follow spin, they don't follow surface cracks, they follow solar geometry, which raises an idea that redefines everything. What if the object isn't just emitting gas because of heat, but because it's receiving instructions from the sun? Solar input, position, magnetism. Each could act as a trigger. In essence, 3I Atlas might not just be a visitor, it could be a listener, an entity or system programmed to respond to specific environmental thresholds. Not alive, not intelligent in the way we imagine, but following a sequence step by step, instruction by instruction, waiting for the right conditions to act. Not random, not reactive, but deliberate, because once you stop thinking in terms of emissions and start thinking in terms of logic, the entire profile of 3I Atlas shifts from natural to designed. In the end, 3I Atlas didn't explode. It didn't send a signal. It didn't shatter into answers. It just kept moving. Cold, silent, and precise. Like something that isn't finished yet. And maybe that's the most unsettling part. Not what it did, but what it's still waiting to do. Because if this was just the setup, then we haven't seen the real story. Not yet.